So now we're looking at evaluating the forces that are acting on the fluid inside the control volume. And there are two types of forces that are shown here. There is what we call the body force that acts on the whole fluid body that's contained within the control volume. So typically that would be mass multiplied by an acceleration term effectively, because how do you get force? It's mass times acceleration. So in that case, we have the mass of the fluid, which is density multiplied by the volume, delta x times delta y. And then we multiply that by the x component of the acceleration of gravity vector, because we're looking at the x component of the force here. If you set up your system so that the coordinate system is aligned with the acceleration of gravity in the y direction, then gx would be 0, but it doesn't have to be the case. So we leave it as undefined. Gx can take a certain value, which is essentially dependent on the way you align your coordinate system. So that's one example of a body force. Other examples could be you have a momentum source of some sort. You may have a turbine or something else that acts, or it could be a magnetic, electromagnetic force or something like that, something that acts on the mass of fluid inside the control volume. After that, we have surface forces. That is, instead of looking at the fluid inside, we look at what happens at these virtual boundaries of the control volume. You have fluid outside and fluid inside. If you have differences in velocity compared or at the interface, it means you will end up generating a shear stress. If you've got compression because you've got more fluid going to the right on the right-hand side of the interface or the boundary instead of the left-hand side, then you can get a compressive stress there that translates into compressive force. So instead of defining each stress right now, we define a framework so that you know what you require in order to determine the force acting on the fluid inside. So that framework essentially involves defining the direction of stresses. And I'm going to revert back to a sketch in order to provide an example or to explain this. Okay, so we have our control volume. And we know there's fluids flowing all around the control volume through the boundaries and so on. And again, we'll follow the same principle. That is, we assume that what happens over a particular phase is the same over the whole phase and can be approximated in terms of the value of whatever physical quantity we track, its value at the center of the phases. Okay, so we show the center with those dots there. So for example, if we know we have a fluid that flows to the right with a certain velocity profile, the profile essentially is a way of representing the variation in velocity along a certain direction. So if the direction of interest here is the y direction, how does the velocity in the x direction change as you move along the y direction? You know that you can represent that change in terms of the first derivative of, or the partial derivative of u with respect to y. And at any stage or any level, for example, between these two lines here, that is between that line and that line, at the interface, you can measure the shear stress as being proportional to that velocity gradient. And the shear stress is going to be written tau yx, which means tau is used to mean shear stress in the direction perpendicular to y and in the x direction. So you end up with two definitions of direction. In 2D, doesn't matter. Essentially, we will have a shear stress at that point that would be along this direction. But in 3D, you have to define two directions in order to define a plane of stress applicable, or where the stress is being applied and the direction in which it is going to be felt. So you define the plane and the direction. So that's why you need these two components. And the way you read it, it means in the direction perpendicular to y, and in that case, in the direction x. If you have the third direction, you could be perpendicular to the y, but in the direction perpendicular to the plane that we see here. So that's the way you read that notation. So for this particular problem there, where you have fluid flowing only in the x direction, and that velocity in the x direction varying in the y direction, then the shear stress felt right here would be equal to the value of that gradient right here multiplied by the dynamic viscosity of your fluid. You would have the same thing down here. If you have the same flow, then you would have again a shear stress appearing like this one, where you would have the shear stress at that point is equal to, again, u over dy. Okay. In both cases, we see that the derivative of u with respect to y is positive, and the derivative of u with respect to y is positive. That means simply u increases as y increases along this direction. Same here, u increases as y increases. We see the arrow become longer. So that would mean that the shear stress on the fluid inside the control volume would appear to be positive in both cases. That's not physically the case, right? If you look at this, think about it. If you're right there on that face and you want to know the force felt by the fluid inside the control volume due to that shear stress here, you have a higher velocity above than below. It means the fluid above is pulling on the fluid inside the control volume to the right. Okay, so we should really have a shear stress which points in the direction of increasing x in this case. Whereas if you go down here, the velocity on the outside of the control volume is slower than just inside the control volume. Therefore, the fluid on the outside or at the interface is going to pull the fluid inside to the left in the opposite direction. We have two definitions that give the same sign, but the direction is actually opposites. So what we do, and there are different ways of showing that, is that we define a convention for the sign of application that fits our physical definition or mathematical definition of the stresses. Stresses here is going to point, if it's positive, it points to the right. If it's positive, it points to the left. And then we do the same in the other direction, okay? So that's the origin of that sign convention. So if I go back to my PowerPoint presentation, you understand now the direction of these arrows to the right and to the left. And then for the compressive stresses, it's always pointing outwards. Okay, the pressure always points inwards. What all this represents are the stresses acting on the fluid inside the control volume over the faces due to the fluid outside. So the fluid outside impacting on the fluid inside the control volume, and those are determined in terms of stresses: pressure, compressive stress, shear stresses. What matters when it comes to the force acting on the fluid inside is the balance between all of these. So if we imagine that the only stresses that are important are this one and this one, let's assume the rest is not important. You focus on that and that. The force due to a stress is the stress multiplied by the area. So you multiply that stress here by the area there, and that stress by the area there, and you look at the balance. This one pulls to the right, this one pulls to the left. The force in the x direction is positive if it goes in the direction of increasing x. So the force Fx due to these two stresses would be this multiplied by delta x minus this multiplied by delta x. And it gives you essentially this term here, because this one and this one cancel out. This multiplied by delta y and delta x. You recognize why we have this term here. If we know the value of the stress here, it will have changed by the time you go there by an amount proportional to the rate of change of the shear stress with respect to y. So we've just explained this and this, and you can do the same for all the other ones. We have a shear stress along that direction and along that direction. We've got a compressive stress in the x direction, which we write with sigma xx compressive stress. And by definition, by convention, they're defined positive if they go outwards. Pressure is in the opposite direction. Pressure always acts onto the fluid inside the control volume. So how do we work with that? Well, we do just what I said in the previous one. That is, the force in the x direction is this minus this, multiplied by the area delta x. Look at the next one. This is what gives us this term there, multiplied by delta x, delta y. I just mentioned it. All this, by the way, is derived in the lecture notes, so I'm not going into each step. If you do the same with the other stresses, we have compressive stress plus pressure, but pressure goes in the opposite direction to the compressive stress. And you've got a sketch representation of what a compressive stress is. Positive, actually, if it's an expansion, so probably shouldn't call them compressive, but essentially they're positive if they actually expand. Shear stress lead to a deformation of a control volume or the volume of fluid that would be originally like a square. If you end up with these positive stresses, you end up with a deformation of this nature. So you can measure it in terms of these velocity gradients. So I'm not actually going through the proof of that. It's available in most textbooks. And you will see that all of these stresses can be represented in this way. If you remember, when we're looking at the previous actually sketch, it's this one. No, it's the previous one. No, it was this one, sorry. You see sigma mu multiplied by du over dy. We have mu multiplied by, sorry, where is mu multiplied by du over dy, okay? This second terms accounts for the effect from change in v over dx, so as you move along the x direction, okay? So it comes from essentially the contribution here. So this one is the contribution here, and dyx is the contribution here. There's a proof again of this symmetry there, dxy or dxy equal to tau yx. Okay? We can provide a proof which we don't give here. So all I'm pointing out here is that we have a definition for the stresses as a function of gradients in the velocity components, and that's the important point there. Because when you sub that in our momentum conservation equation, we've proven that the force on x is going to lead to a change in velocity, and we now have a way of expressing that force in terms of the stresses, which can then be defined in terms of the velocity gradients. And if you sub this definition, you end up with this momentum conservation equation, which relates velocity in the x direction and y direction with pressure. And these come from the stresses or the shear stresses, and you've got the body force. So that's an expression of momentum conservation for an unsteady, incompressible, or fluid flow, which has constant density, I should say, and constant viscosity. So the first thing you should see when you see an equation like this one is obviously you see the complexity of the mathematical representation, but you should remove that layer of abstraction and zone in on the physical meaning. We have a pressure force, we've got a shear stress acting on the fluid, and we have a body force. The combined effect of all these forces is going to lead to a change in the linear momentum, which is expressed in terms of a time rate of change of velocity and a change in the spatial distribution of velocity. You can repeat the same for the Y momentum conservation equation, which is not done on the slides, but it's done in the lecture notes. And the combination of the X and Y momentum conservation equation plus the continuity equation is what define the governing equation of fluid mechanics, where we don't account for temperature effects and we only look at two-dimensional representation. You could do the same for three-dimension. There's nothing fundamentally different in the derivation of the equations. And that concludes the derivation of continuity and momentum, which are governing equation for fluid mechanics. I should though highlight that what you end up with, and I'll pull out the lecture notes to discuss this. We have at the very end our governing equations, which can be expressed in Cartesian coordinate system in 2 dimensions here, which need to be complemented by the continuity equation, which I'm looking for. It's not given here, so I'm just going to write it briefly. And you know we can substitute 3D. Not the full one are not written there, so I'm just going to write them down one by one. We have the Y momentum conservation equation, the X momentum conservation equation, and then we have the continuity equation, which is mass conservation, which would be d rho over dt plus, if we are a general rho u And then ended up with copying it twice. Okay, if you're incompressible, if the density is constant as is shown here, it means you can take it out of the derivative. So here we've made that assumption, density is uniform, therefore it doesn't change also with, if it's constant, it won't change with time, therefore this is going to be 0. And you can take the density out of the derivative. Same here. Therefore, you can divide it throughout by density. Since we have a 0 on the right-hand side, the density disappears. And you're left with just du and dv. So this top equation is called the continuity equation. This one is the x momentum conservation equation, and this one is the y momentum conservation equation. The three together form the Navier-Stokes system of equation. And you have to ensure that when you're looking for a solution, that is values for u, v, and pressure everywhere in space and time, you need to make sure that at any point and in space and time, the three equations are satisfied simultaneously. And what we mean by that is if you were to substitute the value of u, v, and pressure in the equation at every point in space and time, you would get here the left-hand side equal to 0. The left-hand side would have to be equal to the right-hand side. Left-hand side has to be equal to the right-hand side, all simultaneously. The equations are coupled to mimic the physical coupling between pressure and velocity. Simply, if you change pressure somewhere, it's going to impact velocity elsewhere, and vice versa. So mathematically, you need to make sure all three are solved in a way that satisfies all of them simultaneously. That's the final point.